What if I told you that a plane with just one aisle is about to reshape global aviation? On June 15, 2022, the Airbus A321XLR quietly completed its first test flight. No big celebration, no dramatic unveiling, just 4.5 hours cruising smoothly over European skies. To the average observer, it might have looked like an ordinary A321, but in reality, this moment marked the start of a revolution in commercial aviation. This isn't just another upgrade or small improvement. It's a paradigm shift. Imagine a narrow, single-aisle jet that can fly almost as far as much larger wide-body aircraft, but at a fraction of the cost to operate. That's exactly why this aircraft has insiders buzzing. But why is the A321XLR such a game-changer? And what makes it the most strategically important commercial jet of the decade? To answer that, we need to rewind and see how we got here. When jetliners first conquered long distances, you didn't actually need a massive aircraft to cross oceans. The Boeing 707 and DC-8, both single-aisle designs, regularly flew across the Atlantic. These slender jets, despite their size, had impressive range. Then came aviation's golden era. The 1970s introduced the wide-body giants, the Boeing 747, DC-10, and Lockheed L-1011 TriStar. These double-aisle aircraft offered roomy cabins and, just as important, cavernous cargo space that could carry freight by the ton. Airbus entered the competition in 1974 with its first commercial jet, the A320, also a wide-body. But it was their bold decision a decade later that reshaped aviation forever. In 1984, Airbus launched the A320 program, a narrow-body designed to challenge Boeing's popular 737. At first glance, it looked like just another single-aisle jet. But in reality, it became the foundation of the most successful aircraft family in aviation history. And that success connects directly to a question airlines never stop asking. Why are they so obsessed with fuel ethic? ENC. Fuel, it's the lifeblood of aviation, and for airlines, it's also their biggest headache. On average, it makes up 30% of operating costs. That means even a 1% boost in efficiency can translate into millions saved every year. By the early 2010s, with oil prices climbing and environmental concerns mounting, Airbus saw an opportunity. In 2010, they unveiled the A320neo family, NEO standing for New Engine Option. These were just slightly better engines. The Pratt & Whitney PW1000G and CFM LEAP-18 power plants delivered a jaw-dropping 15 to 20% reduction in fuel burn, slashed emissions, and cut noise footprints by 50%. For airlines, the math was undeniable. Each NEO-equipped aircraft saved operators massive fuel costs compared to older models. The upgrade covered the A319, A320, and A321. Only the smallest sibling, the A318, was left behind. Its poor sales simply couldn't justify the investment. But the real breakthrough came in 2018, when Airbus stretched the family's capabilities again. Enter the A321LR, the long range, by adding 3 additional center tanks acts beneath the cabin floor. Engineers extended the jet's reach to an impressive 4,000 nautical miles. But it wasn't just about carrying more fuel. The LR earned ETOPS 180 certification, meaning it could safely fly routes up to 3 hours from the nearest diversion airport, even if one engine failed suddenly. Routes once dominated by wide-body aircraft, like transatlantic crossings, were within reach of a single-aisle jet. For airlines, that meant lower costs, more flexibility, and new route opportunities. And yet, almost immediately, operators asked Airbus for more. Could they stretch this concept to its absolute limits? The answer arrived at the 2019 Paris Air Show. The A321XLR, extra long range, this wasn't just another tweak. It promised something aviation had never seen before, a single-aisle jet with a range of 4,700 nautical miles. Think about the routes now within reach. Perth to the Maldives, London to Delhi, Singapore to Tokyo. The breakthrough that unlocked this capability? The rear center tank, the RCT. Unlike the removable additional center tanks, ACTs, used in the A321LR, The XLR's RCT is a permanent, fully integrated fuel tank mounted just behind the wing box. And here's the genius. This single tank replaces for ACTs, yet only adds the weight equivalent of one, while occupying the space of just two. The result is extraordinary: greater range, more payload capacity, and crucially, no sacrifice in cargo space. But this raises an important question. If a single-aisle jet can now fly these kinds of missions, what happens to the traditional role of the widebody? And if you're picturing the XLR as just a niche tool for low-cost carriers dabbling in long-haul routes, think. Again, the A321XLR has already attracted over 550 orders from airlines spanning the full spectrum: legacy carriers, low-cost operators, and premium boutique airlines. They all see the same thing: flexibility. Take Aer Lingus. Their Dublin-New York service runs strong in summer, but demand thins in the winter. With the XLR, they can fly their A330s during peak season, then switch to the smaller, more efficient XLR in the off-season, keeping the route alive without hemorrhaging money. Or look at JetBlue. Their A321LRs are configured with just 138 seats, fewer than some regional jets, so they can install their Mint business class suites. The result? A premium, transatlantic experience at fares that compete with wide bodies, while operating at a fraction of the cost. This adaptability, from budget carriers chasing new routes to legacy airlines optimizing capacity, is exactly why the industry has embraced the XLR with such enthusiasm. But every aircraft design comes with trade-offs, and the A321LR revealed a major one: those extra fuel tanks that gave it long-haul range. They took up valuable cargo space for airlines. That created a tough equation. Do you carry more fuel to stretch range, or keep cargo capacity for revenue-generating freight and baggage? Some carriers tried to balance it by cutting seat counts and focusing on premium cabins. Fewer passengers meant fewer bags, which freed up space for both fuel and cargo. It worked, but it wasn't an ideal solution. This limitation showed up clearly in payload range curves, a critical metric airlines use to evaluate performance. With the A321LR, flight planners were constantly crunching numbers. How many passengers can we take? How much cargo can we load? How much fuel is needed? Each choice directly impacted the others, reducing flexibility. On short transatlantic routes, like New York to Lisbon, the math worked fine. But stretch further into Europe, and the compromises grew painful. Add in strong headwinds, and airlines suddenly had to decide whether to offload cargo, cut passenger numbers, or even add a fuel stop. And then, in 2020, the equation changed again, because cargo became more valuable than ever. As passenger demand collapsed, air freight rates skyrocketed. Belly cargo, the freight carried in passenger aircraft, suddenly became a lifeline. On some routes, airlines earned more from what was in the hold than from the people upstairs. Rates sometimes exceeded $5 per kilogram, more than triple pre-pandemic levels. In fact, on certain long-haul services, cargo alone accounted for nearly 40% of total revenue. Airlines that once treated cargo as just extra income suddenly relied on it to stay profitable, even flying wide bodies with half-empty cabins. Because the freight below covered the costs, the problem was simple to state and fiendishly hard to solve. The XLR's integrated rear center tank RCT sits in the airplane's crush zone, the part of the fuselage most likely to absorb energy in a gear-up belly landing. Regulators asked a blunt question: if the airplane survives a hard, high-energy belly landing, will that new tank still be safe? Would it rupture, spill fuel, or otherwise increase risk to the cabin and occupants? ESA demanded more than computer models and optimistic assertions. They required real, empirical proof that the XLR's novel layout wouldn't create a new hazard in a survivable accident, and that forced Airbus to treat the XLR not merely as a fuel efficiency upgrade, but as a structural redesign. Program engineering the fix, protect the fuel, preserve the range. Airbus approached the problem on three fronts: structure, isolation, and testing, structural integration, and hardening. The RCT was redesigned as an integral part of the rear fuselage structure rather than a simple add-on tank. That meant reinforcing nearby frames and bulkheads, shaping load paths so impact energy would be carried around the tank, and adding crush-resistant elements in the keel and belly to absorb forces before they reach the fuel cell. Fuel system isolation and fail-safe plumbing. Engineers inserted multiple layers of protection into the tank plumbing, quick-acting isolation valves, reinforced attachments and fittings, and routing that minimized exposed lines in the crush zone. The tank and its connections were designed so that, even if the airframe was deformed, fuel would be contained or could be safely jettisoned away from the fuselage. Mitigation of flammability risk. Beyond keeping fuel from leaking, Airbus tightened requirements for vapor management and venting so any fuel that did escape would be directed clear of potential ignition sources. Redundant seals and protected vent lines reduced the chance that structural damage could lead to an easily ignitable fuel-air mixture near the passenger area. The one thing money and analysis couldn't replace: the test program. Theory had to be matched by evidence. Airbus and EASA agreed an exhaustive test regime was needed. High-fidelity finite element modeling plus physical trials that simulated the worst credible impacts. The program included component-level destructive tests, full-scale structural tests, and fatigue campaigns to prove the reinforced rear fuselage would behave as predicted over the aircraft's life. Crucially, the testing showed not only that the tank survived specified impact conditions, but also that failures, if they occurred, would be progressive and contained, not catastrophic. That's the difference between an acceptable design and an unacceptable one. You must demonstrate that the aircraft tolerates damage without creating a new disproportionate hazard to occupants or rescue crews. Operational and certification outcomes regulators clearly signaled that meeting the structural and system requirements was non-negotiable. Airbus invested the engineering hours and test budget. The result was a validated architecture that preserved the XLR's range and, critically, kept cargo and baggage space usable. That meant airlines could finally carry long-haul fuel without sacrificing freight revenue, removing the key operational trade-off that hamstrung the LR variant alongside the hardware fixes. Airbus and authorities also agreed operational mitigations, dispatch rules, revised loading procedures, and maintenance inspections focused on the RCT area to assure long-term integrity. In practice, that meant airlines got both a certified safety case and a set of procedures that kept the airplane working reliably in everyday service. Why it mattered solving the crashworthiness question unlocked the XLR's strategic value. Instead of a single-aisle jet that stretched range at the expense of belly revenue, the XLR became a true long-thin workhorse, transcontinental range, wide-body competitive economics on off-peak routes, and enough cargo space to keep critical revenue streams intact. The regulatory scrutiny slowed the program and added cost, but it also forced a cleaner, safer solution. The payoff for airlines was huge, an aircraft that could open many city pair markets profitably without the complexity and fuel burn of full widebodies. For passengers, it meant more non-stop options. For the industry, it meant an aircraft family finally filling the hole left by the Boeing 757, but with 21st century engines, systems, and safety engineering. EASA's demand forced Airbus to move beyond neat spreadsheets and feel-good simulations. Regulators wanted real-world proof that the RCT wouldn't turn a survivable belly landing into a catastrophe. Airbus answered by attacking the problem on three fronts: structure, containment, and verification. First, structural changes routed crash loads around the tank instead of through it. Engineers beefed up the rear keel and redesigned local load paths so that a high-energy impact would be absorbed by reinforced primary structure rather than the fuel cell. In practice, that means the fuselage skin, longerons, and keel act as sacrificial energy paths, preserving the tank's integrity in many realistic gear-up scenarios. Second, the fuel system itself was hardened and isolated. Plumbing and venting were rerouted away from the crush zone. Fittings and valves were upgraded to aviation crash standards, and additional seals and protected manifolds were added so that, if structure deforms, fuel lines won't be sheared or directed toward heat sources. Designers also improved vapor management and added passive mitigations that make any small leak unlikely to accumulate into an ignitable cloud. Third, Airbus didn't stop at theory. They validated it. The company combined high-fidelity finite element modeling with aggressive physical testing, component knockout tests, reinforced structure load trials, and targeted full-scale validation that replicated severe gear-up impacts. Those tests were specifically designed to demonstrate either that the RCT remains intact under survivable impacts or that, if it is damaged, it fails in a controlled way that does not increase risk to passengers or rescue crews. Regulators also insisted on complementary operational controls, revised loading and dispatch rules, targeted inspection tasks for the RCT area, and maintenance intervals focused on detecting fatigue or local damage before it becomes critical. Those procedures don't replace good design. They make the solution robust across years of in-service operations. The upshot, the extra engineering, testing, and procedures added time and cost. But they solved the core problem that threatened the XLR concept. By protecting cargo volume while meeting crashworthiness expectations, the RCT removed the painful trade-off airlines had faced between fuel and freight. That's why the XLR can genuinely offer 757-like mission flexibility with modern fuel burn, and why regulators' insistence on hard proof ultimately made the airplane both safer and more commercially valuable. Exactly, and that's what makes the A321XLR such a fascinating story in modern aviation. Airbus, by pushing the single-aisle platform beyond what many thought possible, has essentially forced the industry to confront a new reality. Revolutionary design is still possible, but it doesn't come without friction. Those redesigned belly fairings illustrate the delicate balancing act, make them strong enough to withstand a gear-up landing while ensuring they deform in a predictable way. Protect the RCT while not adding so much structural weight that performance suffers. It's a razor-thin line between innovation and compromise. The delays caused by these redesigns highlight a larger truth. Modern commercial aircraft programs are rarely about raw engineering breakthroughs alone. They're about satisfying regulators, insurers, operators, and even public perception. Every what-if scenario, no matter how unlikely, has to be engineered, tested, and certified. And that takes time. Yet, despite these hurdles, the XLR has retained its promise, a narrow-body jet with genuine long-haul capabilities, capable of linking secondary city pairs across continents at an operating cost unmatched by any widebody. That's why airlines have stuck with their orders even as timelines shifted. In an era where most new aircraft are simply iterations, quieter engines, slightly better aerodynamics, improved interiors, the XLR stands out as something more radical, a rethink of how airlines can deploy fleets, structure route networks, and balance passenger versus cargo revenue. And that's why, when it finally enters service, it won't just be another new airplane. It'll be a proof point that disruptive ideas can still take flight in an industry that usually plays it safe. Iberia didn't waste any time showing off what the XLR could do. By late 2024, the Spanish flag carrier was already flying it from Madrid to key U.S. destinations like Boston and Washington, D.C. The verdict: impressively quiet cabins, excellent fuel burn, and operating economics that had their finance department smiling. These are the exact kind of long and thin routes, significant distance but moderate demand, where the XLR shines brightest. Hot on their heels, Aer Lingus put the aircraft into service as well, including routes like Dublin to Minneapolis. A perfect example of how the jet can open city pairs that previously couldn't sustain wide-body service. JetBlue is next, planning to roll out their fleet of 13 XLRs across the Atlantic. Think of flights from New York or Boston to smaller European cities that couldn't support an A330 or 787, configured with their signature Mint business class suites. These narrow-bodies will deliver a premium experience while keeping costs far below those of a wide-body. Across the Atlantic, LATAM sees opportunity too. The airline is studying new non-stop links between northern Brazil and southern Europe, flights that bypass the traditional mega hubs in Miami or Madrid. Air Canada has similar ambitions. Their XLRs could connect Toronto with secondary European cities like Funchal, Malaga, and Nantes, opening up non-stop options that simply wouldn't be viable with larger aircraft. And this is just the beginning. American Airlines has its first batch of XLRs arriving soon. Initially, they'll replace the aging A321T fleet on premium U.S. transcontinental routes before stretching their wings internationally. These aircraft will feature next-generation business class suites, a level of comfort once reserved for wide-bodies, now reimagined for a single-aisle jet. Then there's Indigo, India's low-cost powerhouse. With its first delivery scheduled for mid-2025, the airline plans to use the XLR to unlock previously untapped routes across Southeast Asia, Central Asia, and Eastern Europe, markets long dominated by legacy carriers. And the list doesn't stop there. Qantas, Wizz Air, Lufthansa, Jetstar, and even Aer Lingus are all lining up with bold, carefully targeted strategies for their XLR fleets. Each sees the same potential, the ability to connect new dots on the map profitably, with a jet that blurs the line between short-haul efficiency and long-haul reach. Despite some supply chain delays, adoption of the A321XLR across the industry is still picking up speed. And it raises an interesting question. What if you could fly nonstop between cities that never had direct service before? That's exactly what the XLR makes possible. Think about the possibilities. Kansas City to Frankfurt, Chennai to Nairobi, or Perth to the Maldives. Routes that once needed a wide-body aircraft, or simply weren't economical, are suddenly within reach. For airlines, the XLR isn't just another airplane. It's a precise tool, a strategic scalpel in fleet planning. Want to test an unproven route without the financial risk of putting a twin-aisle jet on it? The XLR gives airlines that option. There's also the environmental angle, something airlines can't ignore anymore. Compared to older aircraft flying similar missions, the XLR burns about 30% less fuel per seat. That's a huge improvement for an industry under pressure to reduce its carbon footprint. United Airlines, for example, is already evaluating new non-stop connections between the U.S. and Brazil using the XLR. Saudi carriers see potential in new European destinations that wouldn't support wide-body service. And this is just the beginning of the story. Airlines are closely watching the aircraft's early performance, and Airbus is already thinking about what could come next. Future enhancements might include cabin upgrades, aerodynamic tweaks, or even stretched versions of the jet. Industry analysts are buzzing with speculation. Some talk about a possible A322 with greater seating capacity. Others imagine a Neo Plus, featuring upgraded engines and even more range. But the most intriguing idea floating around is the so-called A321XL. This hypothetical version would add 3 for extra rows of seating while maintaining the XLR's long-range performance. If Airbus went down that path, it would push this narrow-body even deeper into territory traditionally held by smaller wide-bodies like the Boeing 787-8, creating a whole new competitive challenge. Despite some supply chain delays, adoption of the A321XLR across the industry is still picking up speed. And it raises an interesting question. What if you could fly nonstop between cities that never had direct service before? That's exactly what the XLR makes possible. Think about the possibilities. Kansas City to Frankfurt, Chennai to Nairobi, or Perth to the Maldives. Routes that once needed a wide-body aircraft or simply weren't economical are suddenly within reach. For airlines, the XLR isn't just another airplane. It's a precise tool, a strategic scalpel in fleet planning. Want to test an unproven route without the financial risk of putting a twin-aisle jet on it? The XLR gives airlines that option. There's also the environmental angle, something airlines can't ignore anymore. Compared to older aircraft flying similar missions, the XLR burns about 30% less fuel per seat. That's a huge improvement for an industry under pressure to reduce its carbon footprint. United Airlines, for example, is already evaluating new non-stop connections between the U.S. and Brazil using the XLR. Saudi carriers see potential in new European destinations that wouldn't support wide-body service. And this is just the beginning of the story. Airlines are closely watching the aircraft's early performance. And Airbus is already thinking about what could come next. Future enhancements might include cabin upgrades, aerodynamic tweaks, or even stretched versions of the jet. Industry analysts are buzzing with speculation. Some talk about a possible A322 with greater seating capacity. Others imagine a Neo Plus featuring upgraded engines and even more range. But the most intriguing idea floating around is the so-called A321XL. This hypothetical version would add 3 for extra rows of seating while maintaining the XLR's long-range performance. If Airbus went down that path, it would push this narrowbody even deeper into territory traditionally held by smaller widebodies like the Boeing 787-8, creating a whole new competitive challenge. Will passengers paying $3,000 or more for a business class ticket accept a more confined experience than what's available on a wide-body? Ultimately, the market will decide. The A321XLR isn't just another aircraft. It represents the dawn of a new era in global connectivity. Could single-aisle jets like the XLR replace wide-bodies on many long-haul routes? And is this the beginning of the end for the traditional hub-and-spoke airline model? Hub-and-spoke networks have dominated international aviation for decades, concentrating passengers at major airports before redistributing them to their final destinations. But the economics of the XLR could accelerate the rise of direct flights between secondary cities, fundamentally reshaping global travel patterns. The implications extend to airports as well. Many regional facilities currently lack the infrastructure to handle wide-body jets, but they could easily accommodate A321XLR operations. This opens new international gateways without massive investment in infrastructure. The future of aviation is taking shape before our eyes. And it looks remarkably different from what we imagined even a decade ago, while the pandemic accelerated some trends. The rise of the long-range narrowbody was already underway. What we're witnessing isn't a temporary adjustment, it's a fundamental restructuring of how aircraft connect the world. If you enjoyed this deep dive into the aviation industry's most transformative new aircraft, hit that subscribe button and let me know in the comments which aviation topic you'd like us to explore next.